approaches pi over 2 of this expression, problem 37. When I plugged in pi over 2, just kind of to see, hey, is it continuous? I see I get a 0 in the denominator of the bottom fraction, but also I get a 0. Which one of these is 0? Well, if you look at the unit circle and you look at pi over 2, right, this point at the top of the unit circle is 0, 1, right? So this is 1 over 0, right? So as we approach pi over 2 from the negative side, the denominators of each fraction are approaching 0. This is what the book calls infinity over infinity form. Because when you divide by a really small number, your answer gets really big. Does that make sense as far as the start? So this is where, once you have that, something over 0 divided by something over 0, that's an indeterminate form, right? And so now you're allowed to apply L'Hopital's rule. And so apply by L'Hopital's rule, we could say that this equals the limit as x approaches pi over 2 from the negative side. And now what am I going to do? I'm going to take the derivative of the top and take the derivative of the bottom. Right? What's the derivative of the tangent of x? Secant squared x. Now the bottom here, I'm going to have to work it out. It's the derivative of, if it were me, I would write it this way. 3 times, and then I would write this as 2x minus pi to the negative first power. That make sense? Okay, so again, this is the limit as x approaches pi over 2 from the negative side. Here I have secant squared of x still. And then in the denominator, I guess I would write this as, let's see, I need to do bing, bing, bong, right? So ignore the 3, bring the negative 1 out, so that's negative 3 times 2x minus pi, what's the next bing, to the negative second. So there's bing, bing, and then I need to multiply by, which would be 2, bong, right? Bing, bing, bong. This all okay? So, let's see. This is the limit as x approaches pi over 2 from the negative side. It's kind of ugly. I better put it down here. Okay, so this is the limit as x approaches pi over 2 of, now secant squared, we know that that means 1 over cosine of x squared. And then this denominator I could rewrite as negative 6 divided by 2x minus pi squared. So maybe that's how I would write it. So, I have a fraction divided by a fraction. All right. I'm going to plug in my pi over 2. And so I have, let's see, 1 over the cosine of pi over 2 squared. Now, instead of dividing by this fraction, I know that I can multiply by what? The reciprocal. So I can multiply by 2 times pi over 2 minus pi squared over negative 6. So this ugly stuff here, that still equals 0. So I get 0 in the top, and cosine of pi over 2, well, that's still 0, right? Wow, okay. So we did all that work, but we're not there yet, right? I still don't know if the limit exists, but because I got 0 over 0, what can I do now?
Another L'Hopital.
I can do another L'Hopital, so here I go. I'm going to change colors. So L'Hopital again. All right, here I go. So now I have the limit as x approaches pi over 2 from the negative side. Wow, it's funny. I don't see this going anywhere. Because if I take the derivative again, I'll get 2. I'm doing bing, bing, bong here, right? Because this is the numerator is really secant of x squared. So I'm going to get 2 times the secant of x to the first power times the derivative of what's inside. Now, what's the derivative of secant of x? It's secant x tangent of x, yeah. That's a lot of secants, yeah. But then the denominator, if I can work it out again. I would need the derivative of -6, and this was 2x minus pi to the -2nd. It's going to do this forever. So I have a problem here. I'm not quite sure what to do yet. Did you get it, Duncan?
I did.
Good. Limit as x approaches pi over 2 from the negative side. I have tangent of x divided by 3 over 2x minus pi. And so Duncan said, well, wait a minute. Let's write this as the limit as x approaches pi over 2 from the negative side. Instead of dividing by the fraction, let's multiply by the reciprocal right away. So how do you write tangent x as a fraction? It's sine of x over cosine of x. And instead of dividing by this, let's multiply by 2x minus pi over 3. Okay? So again, when I plug in pi over 2, kind of like happened before, I get 1 times 0 over 0 times 3. Instead of getting infinity over infinity, now I get 0 over 0. Right? But it's kind of interesting because now if we apply L'Hopital's rule to the problem, say in this format, right here, things work out nicer. So let's apply L'Hopital. To that mess there. All right. See what happens. We now have the limit as x approaches pi over 2 from the negative side. Tell you what do you want to do first? The numerator or the denominator? Let's do the denominator. That actually looks pretty easy. Because we have 3 cosine x. So what's the derivative of the denominator going to be? If you guys can't do this, we have no hope. Yeah, -3 sine x. Thank you. Right? So there's the denominator. Okay. In the numerator, I'm going to need a product rule to take the derivative of the numerator. right? So I'll call this sine of x is my u and cosine of x is my v. So I'm going to do u prime v. I mean, this 2x minus pi would be my v. So let's see, this would be, the derivative of sine is cosine. So cosine of x times 2x minus pi plus sine of x times what? Times 2. That's better. And so now when I plug in my pi over 2 from the negative side, and again, I'm looking at the unit circle. There's a pi over 2 angle. On the unit circle, that's the point 0, 1. So the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So I get 0 times 0 plus 1 times 2 over negative 3 times 1. And so the limit is negative 2/3. Wow. Pretty interesting how we could work for 7.5 minutes the other way before I realized this is not going anywhere. But by a rewrite, this 0 over 0 form, there's an advantage here over the infinity over infinity form. Okay? And so that's kind of nice to see. Yeah, so that's problem 37. We will keep this solution instead.
I'm thinking that.
All right, let's try 17. So, I mean, again, first thing to do is just check when you plug in 1, what do you get? So again, this is all about trig. It's all about the unit circle. When I talk about pi, so let's see, my picture is this angle. So that's the point negative 1 comma 0. All right, so the numerator I get 4 times 0. The denominator I get negative 1 plus 1, so yes, we do get 0 over 0. Okay? So then, Joe, what do I do now? Yeah, I'm going to apply L'Hopital. And so I now have that this equals the limit as x approaches 1. So what do we get in the top? Well, what's the derivative of sine? Cosine, right? But since this is the sine of pi x, I'll get the cosine of pi x, but I also have to multiply by what? Does this make sense to you guys if I write 4 pi out front?
Yeah, because you're multiplying by.
The 4 was already there. Why did I multiply by pi? That's the derivative of what's inside. That's the chain rule, right? What's the derivative of pi x? Just pi. Kind of like what's the derivative of 7x? Just 7, right? So that's that piece. Now when I take the derivative of the denominator, I would say the derivative of cosine is negative sine, so this will be negative pi sine of pi x, and then plus 1. That's okay? So let's see, when I plug in 1, I'm just taking the cosine of pi, and that's negative 1 from my picture. So the numerator is going to be 4 pi times negative 1, and the denominator is going to be negative pi, and what's the sine of pi? That's 0, right, from the picture again, plus 1, and so I'm getting negative 4 pi as my answer. Okay? Yeah, this is a good review of what we did last time. Any more? Duncan, question? Positive?
No.
Well, the thing is on the bottom, though, right?
By 0.
The bottom ends up being just positive 1. Is that right?
Well, no, cosine of pi is.
Cosine of pi is negative 1.
Yeah, okay.
So it's negative 4 pi on the top, and just positive 1 on the bottom, because that was a plus x. Right?
Okay.
Okay? Good.
It's, you're multiplying the negatives by zero.
We good? We ready for today? Chapter 7, they go back to L'Hopital's rule one more time in this next section. Okay? So, why? Well, some of these they couldn't really do in Chapter 4. They give you a brief review. We just did a brief review. But now they give you new indeterminate forms. Actually, this one we had last time. Remember 0 over 0?
Oh, okay.
Didn't we? There was a problem where you guys asked me
What's zero?
to work with this function
Either here or
because I remember, here, let me write the function down. We had this last time. Wasn't it the, like, x to the square root of x power? Or something like that? Was that it? Well, let's use this as an example. And suppose I asked you, oh yeah, so this is interesting. Can I compute f of 0? That was the question. And Desmos did, remember? Desmos graphed this function, and it said that the answer was 0, 1. This was the picture we had last class. It looked something like that. We know you can't put anything less than 0 because it's not in the domain of the function. But my question was, what happens if you try to plug in 0? You get 0 to the 0 power. And I said, this is an indeterminate form. I mean, one way to think of this is 0 to any power should be 0, but anything to the 0 power should be 1. So what's going on?
It's both 1 and 0.
Well, it can't be,
Yeah.
right?
Can't be, so it's
So it turns out that the function is no, the function is not defined at 0. I would put an open circle here if I were doing the graph. And I would say, but I can compute limit as x approaches 0, say from the positive side of x to the square root of x. And so that's what I want to show you how to do today. How would I compute this limit? So basically, if I write this problem in the following way, okay? If I want to compute that limit, I'm going to do this. I'm going to say that x to the square root of x is equal to, so I'd like to take the natural log of x to the square root of x. But those aren't equal, right? If you take the natural log of something, it's not equal to what it was before. But you're allowed to do this, e to the, right?
because
They undo each other. We know that this is the inverse of the natural log function. So another way to write x to the square root of x is e to the natural log of x to the square root of x power. Now why would I do that? Because now I can take this square root of x and bring it here. Can you bring it here? Does this make sense? So now I have e to the square root of x times the natural log of x. So this is what I have so far. And you'll notice in the book, they're doing the same kind of trick with some of the other problems. Okay? And now the trick is, well, okay. So, the idea is this, okay? The idea. First, we compute limit as x approaches 0 of the square root of x ln of x.
Also, when you write it, it should be negative because you're, you have to approach it from.
The positive side, yeah. On a positive side. So first I'm going to compute this,
X is going negative too.
then apply e. Mike, you get a question? Or is this okay? Okay. Okay. So yeah, I want to compute this limit. What I'm really going to do is compute e to the limit of square root of x ln of x. Because I'll tell you what, when your book does this, they'll probably go from here to here in one step. They will rewrite x to the square root of x as e to the square root of x ln of x. That's kind of like a one-stepper right there to there. Okay? So first we're going to compute this limit, then we apply e. Yeah, question?
It says limit as x approaches 0, right?
It does, yeah. Limit as x approaches 0. Matter of fact, let me write it more clearly down here. Limit as x approaches 0 from the positive side, and again it was square root of x times the ln of x. And you might say, hey, why is this not easy to compute? I mean, can't you plug in a 0 here? Sure. Right? What's the square root of 0? Can you plug in a 0 here, though? No, you can't. But as we get close to 0, what happens to the natural log function? You guys remember what the graph looks like? I mean, if you think about the graph of the natural log, okay, let me graph it for you very quickly here. It goes through 1, 0, right? But as you approach 0, it approaches this asymptote, right? Yeah, you could say that this is a 0 times infinity form, right? This is 0 times negative infinity, okay? So the reason L'Hopital's rule applies is because you can rewrite this now. You could say, well, this equals the limit as x approaches 0 from the positive side. And so maybe I'll write it as ln of x over, and instead of writing square root of x, which is x to the 1/2, I can put it down here and I can write it as x to the negative 1/2. Okay? Is that the way I want to do this? Yeah, I think so. I think this will work. So, you know, now if I plugged in 0, I'd have an infinity over infinity form. But what we, you know, because when you divide by 0, that's like multiplying by infinity, we could say. So now what I do is I apply L'Hopital's rule. And if I apply L'Hopital's rule, I get the limit as x approaches 0 from the positive side. What do you get in the numerator? What's the derivative of the natural log of x? 1 over x. What do we get in the denominator? We get negative 1/2 x to the negative 3/2, okay? So I'd like to put it back together before I plug in the zeros. What I mean by that is, this is the limit as x approaches 0 of, that numerator is 1 over x, but the denominator you could write as negative 1 over 2x to the 3/2. So again, I have two fractions I'm dividing. So let's write it as the limit as x approaches 0 from the positive side of, instead of dividing the fractions, let's write it as 1 over x times, yeah, 2x to the 3/2, positive 3/2, right, over negative 1. And now what can I do with these x's? You can cancel them, right? I mean, you have the limit as x approaches 0 from the positive side, be 1/2 over negative 1. So that's 2 times 0 over negative 1. All that is 0. A lot of work. So what was it we just computed? We computed that the exponent approaches 0. So the original problem, right? This is e to the 0, so the answer is 1, which is what we said it was from the graph, right? We said that this would approach 0, 1. Okay? So I guess the big difference between the problems in Chapter 4 and the problems in this section in Chapter 7 are that you're going to be basically applying a logarithm and applying an exponential. That's the big difference. And so now it's just a matter of I have to practice some of those with you, I think, and then we ought to be in good shape. So I'm going to go ahead and work on problem 20. There it is. You know, again, the first thing I do when I do limits is I try to substitute in and see what happens. And so I would get 1 plus 0 to the 3 over 0 power, right? So you could argue that this is 1 to what? 1 to what power? Well, that's the thing. You can't divide by 0, so we're going to say that's the 1 to the infinity form. You know, and some of this section is just kind of learning what the indeterminate forms are. So that's indeterminate. Now, why is that indeterminate? Well, you know, if you have 1 to any power, it equals 1. But if that exponent is going to infinity, that's going to make things grow. And so they list them here, right? 1 to infinity, 0 to 0 is what we saw last time, and infinity to 0. All those are indeterminate. Then they have this little note for you, okay? So they tell you kind of what to do. L has a certain form, infinity times the natural log of 1. And so that's going to try and tell me what to do. Okay, so here I go. Back to problem 20. Well, let's do it. So again, I'm going to say that what I want to do here is actually compute the limit as x goes to infinity of what? Of e to the, and then are you guys okay if I do this in one step? 3 over x ln of 1 plus 4x. that make sense to you guys? So again, I took the natural log, brought the exponent down, and then did e to the. Is that too fast? How many are with me? Let me see, show of hands. Couple in the back. Question, Jordan?
I just can't read it.
Can't read it. Well, then we got to do something here.
Thank you.
Did that help? Oh, good. I don't know if it's just bad handwriting or small, but it's because I was small. Okay. So this is what I have, right? I bring that 3 over x out front, and I have this. And so again, the idea is, let's compute this limit first, right? We basically have to take the limit of the exponent. Then we'll apply e. Question, Duncan?
Yeah, wait, what? Zero?
What's that?
The limit.
Oh, yeah. Good question. That's just me being silly. This is still 0. No, it's still 0. Thank you. Otherwise, what? Okay. So again, let's look at what I have here. I want to just compute the limit of the exponent. Let's do that. So right now, so let me kind of give you the idea. I'm going to compute L equals the limit as x approaches 0 of the exponent, 3 over x times the natural log of 1 plus 4x, okay? I'll compute L, then the answer is just e to the L. So I'll compute the limit of the exponent. Right now, when I go to compute L, I can see I'm getting the limit as x approaches 0. This is, if I want to write it as one big fraction, it's 3 times the natural log of 1 plus 4x over x, right? So you get 0 in the denominator, and you get 3 times the natural log of 1 in the numerator. But what's the natural log of 1? 0. Again, you guys have to learn the graph of the natural log function. Looks like this. It's asymptotic over here. It goes through 1, 0, right? And then it grows. So that's the picture. So yeah, this is 3 times 0 over 0, so it really is 0 over 0. And that's why, again, we are going to apply L'Hopital's rule. So here I go, using L'Hopital's rule. So L equals, and again, this is using L'Hopital's rule. The limit as x approaches 0. And I can tell you L'Hopital's rule will work here, because what's going to happen in the denominator? You just get a 1. That's nice. What happens in the numerator? Well, let's see. I'll work that one out. I get 3. And what's the derivative of the natural log of 1 plus 4x? It's the fraction 1 over 1 plus 4x, right? Because that's the derivative of natural log. There's only one more thing I need, though. What do I need to multiply by after that? I need the derivative of 1 plus 4x. That's right, which is 4. Okay? So now I'm almost there. This is the limit as x approaches 0 of basically 12 over 1 plus 4x. And so when x goes to 0, this whole thing goes to 12. This whole thing goes to 12. All right? Wow. So what's the answer to the original problem? The original problem, yeah, will have the answer e to the 12th. That's ridiculously large. And I'm about to put Desmos to the test. The limit as x approaches 0 of 1 plus 4x to the 3 over x power must be e to the 12th. Now, e to the 12th, let me get my calculator out too. I mean, when I said it's big, how big is it? Well, it's bigger than 2 to the 12th, right? Which is what? 4,096. So e to the 12th is, wow, look how much bigger it is. And it's only 2 point something to the 12th, right? It's not even 3 to the 12th would be even bigger. 531,000. Okay. So this is about 162,755, right? So now let's put Desmos to the test and see what the graph looks like, right? Here we go, Desmos. See if you can handle 1 plus 4x to the 3 over x power. Should pause while it... Okay, here I go on Desmos. We're going to graph 1 plus 4x to the 3 over x power. Yeah, no, it seems to be having some trouble here because it has this red line. Zoom out. A lot. Well, at least it knows it's really tall. We got to get to 162,000. Can it do that? No, it just like blew up. Because 162,000, it should cross the x-axis right around here. So y equals this, let's say. And then let's try finding, or maybe I'll make it y of x is this. And then let's see if it can find y of 0. It says no, which that's true, it can't. But now if we put in something really small, it says no thank you. Okay, so it's really having difficulty handling this kind of a function. But we can compute the limit using L'Hopital. Interesting. So I'm going to do with you, let's see. As I look at these, I'm interested in problem 34, let's say. Problem 34. And here it says, which of the two functions grows faster? Or state that they have comparable growth rates. Okay, so I'm going to try number 34. And so 34, we have x squared times the natural log of x, and we have x cubed. And I think I'm going to use Desmos here to help while we're at it. Okay. So again, if I go there, I can sketch a couple graphs for you. Let me graph these two. Equals x squared times the natural log of x. Oh boy, my window's awful right now because I was totally zoomed out. So let's get kind of back to a more traditional window. There we go. So you'll notice it looks a lot like a parabola, but we are multiplying each number by the natural log of x. So like, it's not going to go through 2, 4 anymore, right? Matter of fact, it even goes negative. Why does it go negative for a little while? Because we know the natural log function is negative until you get to where? till you get to 1 comma 0, right? If I type in y equals ln of x, right, it's negative until you get to 1 comma 0. Okay, but what we're interested in doing here is comparing this to g of x equals x cubed. So it looks like g of x grows more quickly, right? Does it grow a lot more quickly? Well, here's where zooming out can help. Maybe not, right? Maybe not. Coming in the long run, they both grow very quickly. It kind of depends on my window. All right. But let's go ahead and take a look from an analytics standpoint here. One way to compare growth rates is the following. We can compare the growth rates using L'Hopital's rule. So basically what I do, the idea is this. I compute the limit as x approaches infinity of f of x over g of x. And basically there are some different possibilities. Okay? So suppose I get 0. If I get 0, what does that tell you about the two functions? Well, this would mean that g of x grows much faster. Okay. If I get infinity, what would that tell me? F of x grows much faster. And if I get anything else, I don't care what the limit is, but if it's just some finite number, we say they have comparable growth rates. So that's the idea. So now I'm going to go ahead and try and do the problem here. Use this information, see what we come up with. Okay, so this is what I decided to call f of x, and this is what I decided to call g of x. And so I'm going to compute the limit as x approaches infinity of x squared ln x over x cubed. Right? Right now, by the way, if you plugged in infinity, whatever that means, you would get infinity over infinity. This is the infinity over infinity form. And so I can use L'Hopital's rule. So I'll just put a little LH here. And now I have the limit as x approaches infinity. Denominator's easy, 3x squared. Numerator not so easy, because what rule do I have to use? Product rule, yep. I'll do it. So u prime v would be 2x ln of x, right? Plus uv prime would be x squared times 1 over x. Okay? But this is still an infinity over infinity kind of problem. Okay? Because right now I have, this is the limit as x approaches infinity. The denominator is 3x squared, and the numerator is 2x ln of x plus, if you cancel those x's, you just have plus x. So I'm going to apply L'Hopital again. Applying L'Hopital again. I get this equals the limit as x approaches infinity of, the denominator is 6x. Now the numerator, I have some work to do. I guess because right here I'm seeing a u, that 2x, and I'm seeing a v, that ln of x. So I'll do u prime v plus uv prime again. So I get 2, that's u prime, ln x, plus 2x times 1 over x, that's the, and then plus a 1. All right, so what do I have? I have limit as x approaches infinity of what? Let's see. Yeah, of 2 ln x. This is just plus 2 plus 1, so plus 3 over 6x. All right, I'm getting there. So yeah, let's do derivative of top and bottom again, right? We'll apply L'Hopital's rule one more time. So this is from L'Hopital's again. So now I have the limit as x approaches infinity of, denominator is just 6. What about the numerator? I get 2 times 1 over x plus 3. Now this 2 times 1 over x, this approaches 0. And so I finally get that the limit is equal to 3/6, which is 1/2. So what did I learn? Oh, derivative of 3 is 0. You're right. Not so fast. Not so fast. So what do I get? I get 0 over 6, so I get 0. Ah, that's better. Now, what did I learn? I learned g of x grows much faster, right? So we get faster growth here in the long run. It's funny, it's hard to see from the graph that you have faster growth. I'm zooming out, but I don't see very much. Okay? But in the long run, you do have faster growth here. And the book goes through, this is really kind of nice, and in the discussion, when they talk about growth rates of functions, okay, they do some examples kind of like the one we just did. And they actually obtain a ranking of these different types of functions. Okay, so here are some different functions. It says, use your intuition and rank the classes of functions given above in the order of their growth rates. So maybe we'll pause for a minute and let you guys do that. This is quick check 2 for tonight. Let me pause and have you guys take a look. See if you could decide which are the ones grow the most quickly and the least quickly. So I'd like to think about this prime number function. P of x is x over ln x. And the question is, which grows faster? So let's try and apply this same idea. The number of prime numbers less than x can be approximated. So the number of prime numbers less than 1,000,000 is like 1,000,000 over the natural log of 1,000,000. The number of prime numbers less than 1,000,000,000 is 1,000,000,000 over the natural log of 1,000,000,000. Okay? So the question is, are there infinitely many prime numbers? But what we really want to do is we want to compare these growth rates. And so if I plugged in limit as x approaches infinity, if I just had this, if I plug in infinity, the natural log of it, natural log grows to infinity also, so you'd get infinity over infinity. But the point is, we can do L'Hopital's rule. And if I do, what do I get? I get the limit as x approaches infinity. What do I get? 1 divided by what? 1 over x. So this equals the limit as x approaches infinity of 1 times what? X over 1. And what is that? Yeah. So when x goes to infinity, this equals infinity. And what does that mean? It means two things. Number one, it means x grows much more quickly than ln x. Okay? The growth rate is much stronger. But number two, it also means that there's infinitely many prime numbers. Okay? So if you believe that that function tells you about the number of prime numbers, there are infinitely many. Did you guys know that fact?